Hello and welcome to this lecture on chemical process modeling and simulation. This is the second of three lectures that introduces molecular momentum transport or friction or shear, and also introduces the idea, the property, the fluid property called viscosity that captures the nature of molecular momentum transport in a fluid. The first lecture, we considered a specific example of flow between two parallel plates. And in this second lecture, we are going to consider the example of what is called Couette flow. So again, we are looking at laminar flow of fluids. Couette flow is basically, once again, a flow between two parallel plates with the bottom surface set in motion at a constant velocity. And this surface is, you can assume it to be infinitely long available. And of course, we are looking at a certain length L over which this velocity profile is looked at. But the fluid, the plate is continuously set in motion. So here is a problem. A fluid is confined between two parallel plates and the bottom plate is suddenly set in motion along the x direction at a constant velocity v. Now this can be depicted by this schematic. You see two plates. Okay, the top plate is infinitely wide. By infinitely wide, what I mean is W is much greater than B, which is the distance between the two parallel plates. Now the length of the bottom plate is and the top plate also is taken to be L, though at any point in time this length L is available for this region, the fluid that is confined between these regions. The top plate is stationary, and the coordinate system is indicated as shown at the left bottom corner. That is that point at the entrance point at the left bottom corner is taken to be the origin, and x is the direction, horizontal direction, the direction of flow, direction of motion of the plate. Y is the perpendicular direction towards the top plate, and Z is the direction going, so to speak, into the screen of the device that you are looking at. This presentation, and that is the direction of the width. Now initially, before the bottom plate, bottom surface is set in motion at a constant velocity, the fluid and the two parallel plates are at rest, and therefore the inertial state of the fluid is that of rest. At time t equal to 0, the bottom plate is suddenly set in motion at a constant velocity v, which is simply vx times I. So in other words, the velocity has a magnitude of vx, and the direction of that velocity is along the x direction. Per Newton's first law of motion, once this bottom plate is set in motion, this motion exerts an external contact force on the fluid, which means the fluid should now get to a new inertial state. Sure enough, that happens. It happens first to the immediate layer of fluid particles that are resting on top of the bottom surface. So the bottom surface is there, and on top of that there are a set of fluid particles that are resting, and those particles are the ones to first feel the external contact force. And once again, I would like to remind to you people, to the listeners, that when I say a fluid particle, it does not mean a molecule. I'm saying this from the concept of keeping in mind the concept of continuum. So we are modeling this fluid in a fashion that we can treat all the properties of this fluid as a continuously varying functions in space and time. And for this, we looked at in a previous lecture the model of a flowing fluid, that the Knudsen number should be less than 0.01, which basically means the mean free path for a molecule should be roughly at least 100 times smaller than the characteristic length scale of the system. This basically means a fluid particle is typically of the order of at least a micron in size, and therefore it has a large number of hundreds and thousands of molecules that are present inside that fluid particle, so that we need not consider the fluid as a discrete collection of molecules. We can look at an averaged continuous system where the details of the individual molecules are no longer important. So keeping this in mind, now there are a set of fluid particles, right? Each particle is of a sufficient size that continuum model of fluid applies, right? And so there are a set of fluid particles that are resting on top of the bottom surface, and once the bottom surface is set in motion at a constant velocity v, sure enough, those are the particles that first experience the contact force. These particles are wetting the bottom surface, adhering by secondary bonds with the solid surface, and therefore they will be dragged by the surface and will be transported at the same velocity v. This is the idea of the no slip boundary conditions. The wetting forces, the adhesive forces between the fluid particles and the solid surface would be strong enough, is the assumption, that it is hard to break those bonds compared to cohesive forces, which is basically the forces between one fluid particle and another fluid particle in another layer, and that those bonds are more easily broken and reformed, and therefore there could be sliding or slip motion. One fluid particle can slide or slip past the surface, but a fluid particle that is wetting or adhering to a solid surface finds it more difficult to slip or slide past the solid surface. So this no slip boundary condition will imply that at y equal to 0, remember y equal to 0 is the bottom surface and y equal to plus b is the top surface. So at y equal to 0, the velocity of the fluid particles that are wetting that surface is given by Vx of y is equal to whatever is the velocity with which the bottom plate is set in motion. The fluid particles at any value of y greater than 0, of course less than p, which were stationary, now will be dragged by those particles that are wetting the bottom surface. However, the cohesive forces between these fluid particles are weak enough that the fluid particles at a slightly higher top of the first layer, right, they can slip against or slide against those wetting the bottom surface, and therefore they will not be dragged by the same velocity as that of the bottom surface. So they will flow or move at a slower velocity. In other words, their inertia, which comes from the original rest state that they were in, that inertia holds them back. This basically results in this sliding shear frictional force, again Fxy, between the different layers of the fluid. Why is this Fxy? Because the direction of motion of the fluid is in the x direction, and the force itself is exerted between fluid particles in two different y planes. So this shear frictional force is represented as F with a subscript xy, two directions. Once again, the fluid particles at a specific y will typically all flow at a certain velocity in the x direction. Now, the fluid particles at y is equal to 0, by virtue of no slip condition, will flow at the same velocity as that of the bottom surface. And at higher and higher values of y, the flow rate will gradually, or the velocities will gradually decrease until you reach the top surface, which is stationary, which we will see what no slip results in there. But the idea is that at any value of y, all the fluid particles will flow at a certain velocity along the x direction. In other words, the x velocity Vx of a fluid particle depends on the y position that the particle is at. So if is this particle at y equal to 0, y equal to 0.1b, 0.2b, 0.3b, 0.5b, 0.9b, y equal to b, which is the top plate. Where is it located? The fluid particle located relative to the two surfaces. One being the bottom surface, which is set in motion at a constant velocity v, and the second being the top surface, which is kept stationary. So between these two surfaces, at which value of y this fluid particle is located, and that value of y will determine the x velocity of that fluid particle, and therefore we can say that Vx is a function of y. Eventually, of course, a steady velocity profile will be established. Now, the fluid particles wetting or adhering to the top surface, which is stationary, will not move. Again, because the adhesive forces experienced by those particles with the solid surface are likely greater than the cohesive forces exhibited between basically the one fluid particle at that top layer and the adjacent bottom next layer of fluid particles, right? And therefore there is a no slip condition there at the top surface. At y equal to b, the Vx, the velocity of the fluid at that y equal to b is equal to 0. Those fluid particles in the top layer are stationary, they do not move. Thus, the velocity of the different fluid layers or laminae vary continuously from basically the bottom surface value, which is at y equal to 0, Vx is equal to the same velocity v as that of the bottom surface. From y equal to 0, Vx equal to v, to the top surface, which is y equal to b, Vx equal to 0. So the velocity range is between 0 and v. At y equal to b it is 0, and y equal to 0 it is v. So in this problem, the x momentum of the layer of fluid at y equal to 0 is transported in the direction to the fluid layers above it. In other words, the fluid particle that is flowing at the layer y equal to 0 drags the fluid particles at a layer just above y equal to 0 along with it, and that in turn drags the fluid particle at a layer just above it along with it, and on and on and on until y equal to b. So a positive momentum quantity is the momentum is basically imparted to the fluid particles at higher and higher layers by those particles that are moving at the lower and lower layers. And therefore, until you impart this momentum which reaches the top surface, and the top surface being a solid, it does not slide, it does not move. The amount of momentum that needs to be imparted, the rate at which the momentum is to be imparted, which basically, once again to recall, rate of change of momentum, time rate of change of momentum is force. In other words, the force that you need to apply to make the top surface move, okay, because the bottom surface is moving through this fluid, you have to impart that momentum, impart that force to make the top surface move. That force will be quite large, and unless that force is reached, that top surface is going to keep remaining stationary, and so it is going to keep absorbing this momentum that is transported upwards from y equal to 0 to y equal to b, dissipate the momentum it gains, and it continues to remain stationary. So we once again see that there is the x momentum of each fluid particle at any given layer of y, right? And that x momentum is gradually transmitted in the y direction. So x momentum transport in y direction due to friction or shear or drag. Thus, each fluid layer at all the values of y equal to y greater than 0 gains momentum through shear or friction. In the case of flow between two parallel plates, at the entrance, all the fluid layers entered with a momentum, x momentum. And what happened was, except the center layer, all the layers lost their momentum in the y direction to either of the stationary surfaces, either the top stationary surface or the bottom stationary surface. On the other hand, in this problem, each fluid layer, each fluid particle in every layer at y greater than 0, all these gain momentum from the bottom surface. If the bottom surface is not continuously kept in motion, then the x momentum gained by the different fluid layers will all be transported up to the top surface. And the momentum gained by all layers will ultimately be dissipated by the top surface. And the entire system will reach back to the original state, which is the inertial stationary state. This is akin to taking a glass of water and pouring it on a stationary surface. The water will move for a little while, but since there is no continuous supply of momentum, frictional forces will retard this motion and there will be a puddle of water which becomes stationary. Thus, to compensate for the x momentum transferred in the y direction, we have to continuously keep doing external work. In other words, the bottom surface has to be kept continuously in motion. And that is when you can establish a steady velocity profile where the bottom layer of the fluid particles move at the same velocity, constant velocity as the bottom surface, and the top layer of the fluid, which is adhering, wetting the top surface, remains stationary because the top surface is stationary. And then you have a steady velocity profile between y equal to 0, velocity is v, and y is equal to b, velocity is 0, right? So therefore, continuous external work will have to be done to keep the bottom surface continuously in motion. This will enable a steady state to be reached. And this is something that you see. So when you have a stationary surface and a moving surface adjacent to each other, right? So what happens is you use these lubricants to sort of minimize this friction, to buffer the friction that would be experienced between two solid surfaces, and that friction will be much larger, and it will really it will get dissipated as so much heat, and then eventually it will start causing damage to these machine parts. And therefore what we use is we use these lubricants, which essentially are situations where one part is stationary, the other part is moving, typically at a constant velocity, either a translational motion or a rotational motion, does not matter. All right, and these lubricants exhibit this sort of a Couette flow. This example is captured in the set of schematic that is represented on the left side of the slide. This schematic is from the classic textbook on transport phenomena by Bird, Stewart, and Lightfoot. So you see basically the fluid initially at rest, and then at time t equal to 0, the lower surface is set in motion with a velocity v, and then at short periods of time, the fluids layers that are right above the lower plate are also dragged along, and there is still an unsteady gradual increase in the velocity profile. Then at long times, the steady state velocity profile is established. The layer of fluid that is sitting on the layer of fluid that is wetting or adhering to the moving lower surface will be dragged at the same velocity as that of the lower surface, and that is the no slip. And at the top surface, which is stationary, the layer of the fluid particles that are in contact with the stationary top surface will remain stationary. They will not move. So that is there the velocity is 0, and in between these two values of y, there is a linear variation of the velocity of x, meaning the x direction, velocity in the x direction as a function of the y position. So as I was just saying, the velocity, the x velocity is a function of y position of the fluid particles, and the frictional force is Fyx, that is the rate of transport of momentum in the y direction by molecular momentum transport. That momentum is coming from the x momentum, actually, that is that the fluid particle has, with which it is moving in the x direction. The shear stress is the flux in the y direction of the x momentum, and that is given by tau yx is equal to Fyx by L into W again, L being the length of the bottom plate, the lower plate, and W being the width of the plate. And this, of course, this molecular momentum flux is proportional to the extent to which the x momentum is decreasing as one goes along y, which is basically captured by the velocity, the rate of change of x velocity in the y direction. That would be the velocity gradient, and the proportionality constant between the molecular momentum flux in the y direction and the rate of change of x momentum in the y direction would be the coefficient of viscosity. Once again, it is observed that momentum is transported from a region of high momentum to a region of low momentum. Region of high momentum is the bottom surface, which is y equal to 0, and region of low momentum is the top surface, which is y is equal to capital B. And to obtain this linear velocity profile Vx as a function of y, one has to perform a force balance in an infinitesimal fluid element and then integrate. Of course, we will see how this happens, how the momentum conservation equation is obtained and how it can be used to obtain the velocity profile in the one of the forthcoming lectures. But this is something, performing a balance, momentum balance or rate of momentum transport balance in an infinitesimal fluid element is something that you've been taught and you are familiar with, I assume. Now that brings us to the end of this lecture. If there are any questions, I'll be happy to answer those questions. Once again, you may post those questions either at the comment section below or you can contact me and I'll be happy to answer the questions. Thank you very much for listening to this lecture. You have a wonderful, wonderful day. Thank you.